Hello, Physics 30s. This morning I'd like to work through the notes on it's called the photoelectric effect, but where we're headed in chapter 14 is the evidence for how or why light is a particle. Okay, we've just spent all of chapter 13 with the evidence convincing you that light is a wave. Now we're going to convince you that, or at least show you the evidence that light acts like a particle, or what we call a photon. Okay. So in these notes, it highlights a little bit of history. Um, Beginning at the 1900s, actually, there are some physicists who thought that we'd figured everything out, but there were a couple of phenomena that couldn't be explained by classical or Newtonian physics. And there's three that are listed here. We're going to lightly touch on the first one and then really focus on the second one. The first one is the relationship between an incandescent object and the color of light that it emits. So a hot glowing solid. Okay, we'll talk about that. And then I really want to get into the photoelectric effect. So the very first thing, and there's an excellent video that I posted with this on what's called the ultraviolet catastrophe. I'd really encourage you to watch that because I think it explains really some of the things we're going to talk about right now. The first thing that physicists kind of theorized about was something called a black body. And you should know what that is. It's basically an object that can both perfectly absorb electromagnetic radiation of all wavelengths and then re-emit it perfectly. Okay. I guess they chose black because black objects, I guess, most closely approximate that. Like if you're wearing black clothing, you absorb heat really well. And it arguably could then be re-emitted later. Objects that are white reflect heat. That's why, I don't know if you've ever been to white sandy beaches. The surface, the top part can be hot, but you don't have to go down. You hardly go down deep at all into white sand, and it's cold. Like it's cool because it's been reflecting light. Black, asphalt is just hot in the summer, and so hence the name. But anyway, the idea behind this is that objects that are or the color of an object when it's heated is directly proportional to its temperature, or its the amount of energy it's releasing. So the if it helps you here, these are showing, or let's just go through these. Classical physics basically predicted that hot glowing objects emit a continuous range of wavelengths and therefore a continuous spectrum of colors. And the light, for a given temperature, the light emitted by the object has a range of consistent wavelengths or characteristic wavelengths. Okay, determine how hot it is. So the hotter an object is, the bluer the light it emits. So that's what's kind of weird. We think of red as being hot and blue as being cold when it comes to plumbing, but it's actually the reverse when you look at frequencies of light or colors of light. So I like to maybe even just say here that maybe add this. So, you have Roy G. Biv, and red is the coolest and violet is the hottest. Okay. So anyway, there is a fair bit of complexity here to this. And what physicists found is that their data did not match their theory. Okay. The data they collected on, hot glowing objects and the colors they emitted, it didn't match their theory. And this one does attempt to show its intensity versus wavelength. And you can see here that the classical theory predicted this kind of upwards trend like that. And the evidence, the collected data, actually showed a drop off when it came to wavelength. Now, I've seen this done in a different way, so I'll just show you maybe this if it helps you a little bit. This is definitely a complex topic dealing with thermodynamics, and I haven't wrapped my head around all the complexities of this. But in simple terms, if we change the x-axis to be frequency, okay, instead of wavelength, I guess we could just label it as F. But the y-axis is still intensity. Okay, sorry. And The classical prediction was that if, as the you could say it, as the frequency increased, the intensity would increase, and it's a linear relationship, and that you might expect that to make sense. That as you increase the frequency, then the image should become hotter, the object should be hotter and hotter. But what they found was the actual data, it did initially go up like this, but then it dropped off right around the frequency for ultraviolet light. Okay, so this is where ultraviolet light was, and that drop off was called the ultraviolet catastrophe. Basically, that it didn't match their data. So that's about as enough as I need to know about that, just because it led to a problem that was solved by Max Planck. Now, if I pronounce his name correctly, I think it's Max Planck. He was German, and so I think, though, we kind of butcher his last name, so I have to apologize to the physicists out there, because I basically just I pronounce his last name Planck. But Max Planck, he analyzed that graph that we were just referring to, and he realized that he could solve the problem if he treated the energy in units or chunks, and then the math worked. And so he called those units quanta. Okay. Now, just as a bit of vocabulary, I guess we should say that the word quanta or quantum is singular. Okay. So a quantum is an indivisible unit. Okay. Quanta is plural, and those terms are going to get used kind of in and out here as we discuss these. But he defined energy in terms of quanta, and then he said this smallest amount of energy was called a quantum of energy, and he came up with this expression to solve for that. E equals NHF. E is the energy, as it says. Sorry, it's the energy of the quantum of energy. N is the number of quanta, so it's how many individual units there are. Now, if you look at your formula sheet, you don't have an N. You just have E equals HF. Now, there's other variations of that we'll get to, but just know that this is for one. This is for one quanta. Okay. So anyway, let me just move that over here. So, but H is a constant, and I'll post another video shortly on how Max Planck got this constant. Okay. There's two versions of it, because there's actually two different units for energy, and we've already messed around with both of these actually back a couple chapters. Planck's constant is measured in joule seconds, is one of the units, and that number is right here at 6.63 times 10 to the negative 34 joule seconds. That's one of the versions. The other version you should be prepared to use is the electron volt second version, and so that one is this 4.14 times 10 to the negative 15. Okay, so they're both on your formula sheet. You'll see them, and yes, you'll need to be prepared to convert energy from electron volts into joules, and that conversion is also on your formula sheet. Okay, and then of course, lastly, F is the frequency of the light. Okay, so in case you need a quick reminder on that, I'll maybe just tuck this in up here. We can calculate the energy in electron volts by using this expression from determining voltage and energy. The amount of energy in one electron that is experiencing a voltage of 1 volt, right? If you remember that. So the charge on an electron is 1.6 to the negative 19 coulombs. And if you multiply that by 1 volt, then you get 1.6 times 10 to the negative 19 joules. And that is an amount of energy, but we call that an electron volt, 1 electron volt. And just for proportionality purposes, using electron volts is often way easier because you can compare stuff when you got a smaller number, which is why we use it in the first place. So anyway, as you saw, if you may have seen in the video, Max Planck made this observation, and he didn't really understand. He understood that it worked to explain heat, but he had no idea that it could possibly explain light. And when Albert Einstein, saw Max Planck's work, he recognized that it could explain light. And so, because light is also quantized or made up of indivisible units of energy, so Einstein proposed that light could do the same thing. And this is where the vocabulary of photon comes in. So you see that there. Um, and this really challenged all of the classical physics, which is why a lot of physicists struggled with it until the evidence became very clear that Einstein was correct. So here's a compression of James Clerk Maxwell's electromagnetic wave theory, and then Einstein's revisions of it to account for the fact that light is actually a particle. So this is a good review for Maxwell. All electromagnetic radiation is produced by an accelerating charge. All electromagnetic radiation is generated by changing electric and magnetic fields. The energy is spread out over an expanding wavefront, and energy intensity per area appears to decrease, right? So as you get further away from the source, the intensity seems to decrease, and that makes sense. So Einstein came along and he basically confirmed everything that Maxwell said, but he made this one significant change, that on the wavefront, the energy is not spread out over the whole wavefront. Rather, it's concentrated in lumps or quanta or packets of light called photons. Now, this here is my favorite definition I've ever come across for a photon, okay? And it basically says a photon is a massless, chargeless particle of pure energy. Okay, a photon has no mass and it has no charge. It is 100% energy, but it is a chunk or very discrete unit of energy. Okay, that's what a photon is. So experiments came out shortly after this that verified Einstein's claim, but all Einstein did was say, hey, the same formula that Maxwell used to explain, heat and his energy expression, that applies to a photon. So here it is here. It's the same formula, E equals NHF, but N is the number of photons now. Okay, and you still use Planck's constant, but now it just opened a whole bunch of calculations because you can now consider the frequencies of all the forms of electromagnetic radiation. You can have a radio photon, you can have an infrared photon, a visible light photon. That one probably makes more sense, but you can have ultraviolet photons, X-ray photons, and so on. Okay, so what that really confirms is something we learned earlier, but we didn't have a reason to explain it. If you look at the spectrum, okay, the electromagnetic spectrum, going from, say, well, whatever, we'll just say radio at this end, and we'll say, cosmic at this end, okay, in terms of the range. So if we look at the expression now, E equals HF, okay, just looking at the frequency. So we said that radio waves are very low energy, and they are. They're essentially harmless, but they're very low energy. They have large wavelengths. You get over to cosmic, though, they have high energy. Okay, dangerously high energy, ionizing energy. Actually, it has enough energy to rip electrons off of atoms and make ions. So, if you look at Planck's formula, if we increase the frequency, we also increase the energy. Okay, remember Planck's constant H is just going to stay the same. So as the frequency of the electromagnetic radiation goes up, so does the energy. And that's exactly what we see. Okay, so now we actually have an expression to quantify that. Now, be prepared though, of course, for this as well, and it'll come up later. We can use the universal wave equation, velocity equals frequency times wavelength, and we can solve for frequency as being well, in this case, it's the speed of light. Sorry, let me change that to that's not velocity. Let's just change that to the speed of light, okay? Because we're dealing with photons. So frequency equals the speed of light divided by the wavelength, okay? And we can easily substitute this in for the frequency, and you get a new formula, hc over wavelength. And there it is. So anyway, we can see here that if the wavelength goes down, which it does as you go from left to right, right? If you see mathematically now, if the wavelength goes down, the energy goes up also. Okay, but both of those formulas are on your formula sheet for the energy of a single photon. Remember, it's just one. It's almost as if you can remember, there is a hidden n right there. Okay, in front, because n stands for the number of photons. Typically, we're just going to deal with one photon. You'll see that in the math. But if you have multiple photons, then you can find the energy for one and times it by that massive number in most cases anyway. So what was left, or what remained now, is an opportunity for someone to come out and validate Einstein's theory about photons. And this is where we get into what's called the photoelectric effect. Now, let me just skip ahead just a little bit here. What Einstein was saying is that if light strikes a metal, okay, so the surface of a metal, if that light has energy, but the metal itself typically will absorb that light, okay, or those photons of light coming in, up to a certain point. And what Einstein was proposing is that at a certain point, that metal will start to release electrons, because the energy of the photons coming in, and we could say typically they show a photon as kind of a little squiggly coming in here, but if the energy coming in is great enough, then the metal will release electrons, okay? And they call that photoemission, because a photon produces an electron, okay? So we have a photon coming in, and then it's causing an electron to be emitted. So that's why they call it the photoelectric effect, or photons causing electrons to be emitted, okay? But what Einstein proposed is that because light exists in discrete bundles, there would be a very specific frequency that all metals you would have to reach in order for electrons to come off. That every metal won't just release electrons at any specific or at any frequency. It's a very specific frequency. So Robert Millikan was the man who took up the challenge, and he said, you know what, I'm gonna see if I can actually disprove Einstein. He was really skeptical that it really was anything. And so I'm going to show you his experiment, and this is what is highlighted. This is what is highlighted up here, okay, in your notes right here. I'll just explain it quickly, and then I'll get to an animation that shows it. So what it is, you need a tube. You need a tube that has no air in it. It has to be a vacuum tube, otherwise the electrons will bump into gas and stuff. So that's what this blue box is right here. And you basically can hook up two terminals. You have a cathode and an anode. And in physics, the cathode is considered to be negative. And you can see that here from the power source here. This is negative and this is positive in the power source. So this cathode right here becomes negatively charged, and the anode over here is positive. So what Robert Millikan did is he shone light, so photons, through the glass and hit the cathode with it. And as he changed the light and the frequency and the intensity of the light, he could get electrons to be emitted from this cathode. And if any electrons got emitted, so they're now free, they would be repelled by the cathode and attracted to the anode. And they would then fly over to the anode. Okay. Now there's some other things we can do with that, but so let's actually just show you that apparatus. It's right here. So let's turn this on. Okay, so you can see this here. I'm going to turn on the intensity. We'll just get the intensity up to 100%. Intensity means more of the same thing. That'll make sense as we get looking at this. Right now, there doesn't seem to be anything happening. And actually, let's go back to, I'll click this back to sodium. So the plate, if you can see it, the plate is right here. This would be the cathode. Here's the anode. And we're going to put a metal plate on the cathode. And right now I've chosen sodium. So I'm shining light on this at 100%. And as you can see, I'm changing the light from infrared. I got into red. Now I'm pushing into orange. Nothing is happening though. And what Millikan realized is that every metal would start to release electrons at a certain frequency. And so now look at this. I'm starting to get some electrons. Obviously, you wouldn't see the electrons. This is an animation. But actually, the way though that Millikan knew he was getting electrons coming off is there would be a current flowing. Okay. So you can see that down here. This is showing a current of 0.017 at the moment. And this is evidence that electrons are being emitted from the cathode. Okay, so we can just change metals here for a bit just to make a point. So I just switched metals to platinum. Now platinum holds onto its electrons much more strongly than what was the first one? Sodium. Yes. So the same amount of energy from, I guess this is blue light, it doesn't do anything for this. So we have to keep in, we're actually going to really move through the wavelengths or frequencies. Look at that, we're out of visible light now. I'm in ultraviolet, and there aren't any electrons coming off. So I think we have to get somewhere in the ultraviolet range. Again, this is an animation, but it definitely mirrors what actually happens. Look at that, we got to punch way down 155 nanometers, in that range before electrons will be emitted. But this is again photo emission. A photon is striking the metal surface and it's causing an electron to be ejected. And really the photons, truthfully, the photons are being absorbed. So all of that energy that the photon has coming in, that's being absorbed by the metal. And at a certain point, then the metal releases electrons. Okay, so in this process, there's a couple of principles. I may come back to this animation to just reinforce some things, but let's go back to the notes and let's look at the data from this experiment. So what was found is, in order for any photon or for any photons to be emitted, you must have a high enough frequency for that metal. Einstein proposed that would be called a threshold frequency. Okay, here it is noted down here. It's called the threshold frequency, and it has a symbol F0. Okay, now you'll see that in the formulas as we go. It's just, it's a special frequency, but it should make sense that it's the threshold frequency. Okay, and I'll actually show you that in a second when we go back to the animation. Classical physics couldn't explain that. They thought that, as soon as electrons start hitting a metal, the metal should start warming up and it could start releasing electrons at any temperature or at any frequency. But that wasn't the case. It was always very specific. And so that kind of refuted some of the classical physics. Okay, so the second observation, once the frequency is greater than the threshold frequency, then the instant the EMR is shone on the metal, the photoelectron emission is immediate. Okay, so as soon as you, like, if I know that I'm above the threshold frequency, the instant the light hits, electrons come off, like instantly. And that was also not explained by classical physics. They thought there should be some time there where the metal would absorb it and kind of warm up and then let go. And it didn't happen. So that classical physics couldn't explain that. Now, these last two are really important, as you'll see a little bit later. As the intensity, okay, so there's that word, as the intensity is increased, and if that helps you, that means more of the same thing. Okay, so that would be like, instead of having one light bulb, one red light bulb, you could have 10, okay, 10 red light bulbs. Okay, so if you increase the intensity, what was noted is that the number of electrons, photoelectrons, they're calling them, increased, and the current increased too. Okay, so that kind of makes sense. But what didn't happen though is, or what was a little bit weird, is that you have more electrons coming off, but they're not coming off with more kinetic energy. Like, they're not coming off faster. Like, you would just get more electrons that would come out. They'd all come out at the same speed, but they like, having more intensity doesn't mean that they come off faster. I mean, that may not make sense just yet, but I'll try and show you that in just a second. Anyway, that was another thing that classical physics couldn't explain, but the particle theory or quantum theory did. Okay, and then this last one, as the frequency of the incident EMR increased, they noticed that the kinetic energy, so the speed of the emitted electrons, increased as well. Okay, and that didn't make sense with classical physics either. Okay, so let's actually go back quick to the animation, and we'll try and make sense of what that was. Okay, so here we'll just run that. Let's actually go back to let's pick a different metal here, zinc. And I think zinc had actually, let's do a couple of things here. So on my little graph here, if you can see it, this graph shows frequency on the x-axis and energy on the y-axis. And as I move the frequency, okay, so I'm getting higher and higher frequencies. Okay, you can see on the x-axis that's moving. There's no energy for the ejected electrons, because there aren't any electrons coming out. But watch, as soon as I hit, see there on the x-axis there, as soon as I hit a certain frequency, then I start getting electrons coming out with some energy. Okay, and so you can see I can move that graph. I can move at any different points on that graph and plot the data on that graph. What is really interesting here is, as soon as there is energy right on that x-axis, that there is the threshold frequency F0. Okay, that's the frequency. That's the one that you must get to before you're going to see anything. Okay, and so, actually, I'm at 100% already. So let me just change that. Let's go to like 40. Let's drop it down to say like 34% or something. Let me make sure I just get in here so you can see enough of what's happening. Okay, so here you can see I'm getting, look, there goes 3 electrons that were fast. I'm getting some electrons that are slow. Okay, and really all we care about, I'm going to turn this on, all we really care about is the highest energy electrons. Okay, I'm just going to let those clear out, because you won't get a current flow down here like an ammeter. You won't get a current flow unless you have some electrons coming out. Now, actually, there's a little flaw in this animation, because we're seeing electrons come in and the current's reading 0. Okay, but anyway, let me just adjust that just a tiny bit. Okay, so there, that's a little more believable. Okay, so the point is, if you can see relatively, these electrons that do get emitted are coming out at the same speed, okay, as they make their way across. If I increase the intensity, I'm only at 34% here. If I increase that intensity, let's just go way up to 100 here, you'll notice actually that the electrons coming off are not going any faster. Okay, and this animation isn't great, but the idea here is that I'm getting more electrons coming out. There's more electrons being emitted, And so the current has gone up. You see that it's now 0.047, whatever it was before. But the electrons being emitted do not have a faster speed. They're not traveling faster. Okay. And we call that the kinetic energy. Okay. So, what else do I want to show you? Oh, okay. So, what Robert Millikan did here is he realized that he could actually measure the kinetic energy of these electrons. Again, how are you going to do that? Because you can't see them. So he came up with a clever. That's what this. That's what this battery is here. What he did is he actually charged up, and I'm starting to do it right now. He charged up the negative, or he charged up the anode with a negative charge. So he purposely ran current to this to the anode and also to the cathode, making this negative. And well, he did that in increments, okay, such that he did it in increments until the current read zero. Okay, actually, I kind of got it right here. So the photoelectric effect's happening at the cathode here. So electrons are getting, shot, like ejected from the metal, but they are not quite making it to the cathode now because I'm charging it negative. I've charged that plate negative. So if I charge it just to the right amount, the electrons they won't quite make it. And the evidence for that is that the current would drop down to zero. Okay, so that's at 0.6. See, so if I shut this right off, put it to zero, I've got a current of 0.047. But just moving it over enough, now, let's see, the animation has a glitch in it. Yeah, I guess I got to go to 0.6. So now if I go to 0.6, now look at that. Okay, the electrons are not quite making it, okay, to the other terminal. And so what Millikan realized is he could calculate the energy of these electrons with the formula that we mentioned earlier. The energy would equal the charge on the electron times the voltage. Okay, so you got this voltage here of 0.6. And he gave that a special name. He called it the stopping voltage because this is exactly what it's doing, right? It's stopping the electrons from reaching the negative plate. So let's go back to the notes, and I want to show you how or where that comes into play here. So these notes actually just kind of reinforce the formula for a photon. They also list the formula for the work function. The work function is really the amount of energy associated with the threshold frequency. Okay, so work function is equal to H times F0. And remember, F0 is different for every metal. I could show you some more of those in a little bit. So every metal has its own work function. Okay, now this is where we get down to the big expression. And this here, this expression here is useful, but I find it's a little clunky in terms of making sense of energy. So I'm going to rewrite it over here. The total interaction that's happening here is the energy of the photon coming in has to equal the energy absorbed by the metal and whatever's left over in the electron that's ejected. So the big picture is that the energy coming in has to equal the energy going out. The energy that comes in to this interaction is the photon. Okay, so I'm just going to write this quickly. The photon has all of the incoming energy. The outgoing energy is some of that energy is absorbed by the metal. And then if there's any left over, like if we've reached the work function of the metal, then there is some kinetic energy in the electron that's emitted. And we call those photoelectrons. They're really electrons. We give them that name photoelectron because they're the result of the photoelectric effect. But if you see the word photoelectron, don't trip on that. It's just an electron, okay? Now, this is the expression then. The energy of the photon can be written as HF. The energy that the metal absorbs is the work function, which you just saw above. and the energy of the electron, we call it EK max, because we really are only concerned with the maximum energy of um, the ejected electron. Okay. The other electrons that are coming out a little bit slower for whatever reason, they're not going to cause the current to start. And so we really don't worry about those too much. As soon as we see electrons, then we know we can measure those. Okay. So now, when I told you that Millikan came up with that stopping voltage, he came up with this expression, and I'll just tuck it down here for now. The EK max, the maximum kinetic energy, is equal to QV stop. Okay? Energy is equal to Q times V. We've already used that, but Millikan realized that using that setup, so you can see it right there, EK max will equal the charge of the electron times the stopping voltage, or how much voltage you had to apply to that plate, the anode in that case, to stop the electrons from getting there. So working backwards, he could then solve for the velocity of the electron, which you are going to do a number of times as we go through this. Okay, so that means there's there's a couple of versions of the photoelectric formula that you need to know, and I would strongly encourage you to write these on your formula sheet, because your formula sheet only has the pieces. It has the formula for the work function, it has a formula for a photon, and it has the formula for the stopping voltage, or sorry, for the EK max. It has all three of those, but it doesn't put them together. So the other version, I guess we could also express the energy of the photon as hc over wavelength. Okay. And we can express the work function as hf0, and we could express the kinetic, or maximum kinetic energy, as qv stop. Okay. Now, all of these parts are interchangeable, but this right here, the idea, I guess, that energy in is equal to energy out, and the fact that you have a couple different variations, I would add those to your formula sheet. And these guys right here are going to help you a lot when you're analyzing this. Okay. So yeah, the HF is equal to W plus EK max, or HC over wavelength is going to equal HF0 plus QV stop. Both of those are the photoelectric effect formulas. Okay. So what's left here on the notes, this actually shows the work functions of some different metals, just determined experimentally. And that's actually how we, if we were to graph all of these, which I'll post a separate video on, we can actually determine Planck's constant from that. Okay. So where we're headed here are these practice questions right here, and I'm going to post the answers to them shortly. But I just want you to see, just carefully as you read through these, you're going to be using the photoelectric effect formula. Okay. So again, in reminder, it's either HF is equal to HF0, this is one version, plus EK max, or you could use any of the other ones, HC over wavelength. If maybe you just were given the work function, then you could use just that, or you could exchange EK max for QV stop if you were given QV stop. Okay, so identify all the variables and work through it slowly, and I'll also post the answers here right away.